SAT340 week 7. So this week we will have a look at problems without full rank, as I have called them. And what is this? This is a type of problems where we cannot use the linear model theory that we have learned so far for some particular reason. And that is what we will look a little bit into, the lack of full rank. And first let's see how we can detect this problem, because it's a problem that comes in combination with data and model. Two of the methods that we will look at for handling such problems, the PCR and the PLS methods. And PCR is simply principal component regression, and this is partial least squares. They are sort of related, so I will sort of treat them together. We will see a little bit of how we can form predictors from the predictors and form new predictors, actually called components here. And then cross-validation, we saw that last week, we will see that again here now. And finally, how do we sort of find the significant effects using these methods here? And that is not really straightforward, because they are not really built for that purpose. But I was thinking that this is a proper occasion for us to introduce bootstrapping. This is not the only way to do this, but bootstrapping is a technique you should know about. So I thought that this was a proper place to introduce bootstrapping to you, even if this is not strictly the only way to talk about significant effects with these methods. There are some other solutions too, but we will not talk about that. And then last week we saw the lasso method for variable selection and the elastic net. This is just a small extension of lasso, actually, and we will see. And why should we extend lasso? Well, when we have this type of problems, lasso is shown to be not the best. But if we make this small extension here, we have some possibility to fix that. So this is still a method that we may use even for these lack of full rank problems. So what do we mean about full rank? Well, it has to do with the ordinary least square estimation procedure, and this is very technical, so I will just mention it here now. We will not dig into it, because we cannot assume everyone to have the mathematics that it takes to explain this. But let me show you the matrix notation. We have previously seen we write our data sets like this, right? We have a response variable, a column here, and then we have some predictor variables over here, some columns. And of course we can write this as a vector y. We use it boldface, so it means a column, not a single value, but a whole column, right? And the matrix X, that is simply just as you can say a vector of columns again. So you have first vector here, second, third, and so on, and then it's a matrix with boldface again. And then the linear model can actually be written like this. All the responses here is simply this matrix, and this is an inner product multiplication with a corresponding regression coefficient vector here, which is then simply all the regression coefficients gathered together like a column here, or a row, right? It's a column, actually. It's just drawn as a row here. And then you have all the error terms here. So this is just a matrix way of writing the same model that we have seen all the time. And then it turns out that estimating the parameters, solving the least square problem, is done by solving this equation. This is called the normal equations. And here you can see we use the transpose operator, and we used the inversion operator and so on these matrices here. So if you don't know what this means, don't panic, because I just show this because what the lack of full rank means is that we have a problem here. this problem can only be solved if this matrix here has full rank, because if it doesn't have full rank, we cannot invert it. So then we have no solution actually here. And full rank, what does it mean to have a full rank? Well, what does it mean to not have a full rank? We do not have a full rank if any predictor in here can be written as a linear combination of the other predictors. If one of the columns can be not just it's not just similar, but is identical to a combination of the other columns. And especially if two columns are identical, then this is true, right? And then you have lack of full rank. But also if one column is the sum of some other columns, right? Then you also have this lack of full rank. Or any other linear combination, right? You can take 2 times one column minus 3 times another column plus 4.5 times the fourth column, and so on, right? You can build this linear. If there is any way you can build a linear combination where one column is a combination of the others, then you have this problem here. This is always the case when p is larger than n. And what do I mean by p larger than n? Yeah, p is the number of columns, right? You can see here from the notation, right? This is column 1 up to column p. So we have p columns, and n is the number of rows, data cases. And if you have more columns than you have rows, if this matrix is sort of wide but not so very tall, then you have this problem. You don't have to sort of test it. I can tell you right away, it's mathematically impossible not to have that problem. So this is the common reason for the lack of full rank, that we have more predictors than we have observations. And that happens quite frequently, I would say, in our world these days. I mean, we collect data in vast amounts. And many of these technologies that we make use of these days allow us to collect a lot of information, a lot of columns, right? Many variables. So for in many sciences and in many applications outside science as well, we come across this type of problems. I see them all the time, where we have thousands even of columns, but we have only perhaps some tens or 100 rows, right, in our data sets. Because collecting new rows is expensive, but collecting many variables is cheap. So that is one way we can arrive at such a problem. We should also be aware that even if we have a full rank mathematically, we still have a problem whenever we are getting close to this, losing the full rank. And so that means if you have p almost as large as n, then you also have a problem, not as acute, but still a problem, because estimates get bigger and bigger variances as p grows when n is fixed. And then it explodes into infinity when you cross that limit here. So actually, what this problem tells us is that when you lose the full rank, you no longer have a unique solution to this equation. That's the problem. It's not like you have infinite many solutions to this problem actually. So you don't know which one to choose. That is actually the problem. And even before you reach that critical limit, you run into problems because the variances get bigger and bigger and bigger as you get a bigger p with a fixed n. And this is exactly, we have actually seen this before, because this is a problem that arises when models meet data. That's important to know. It's not the model in itself which is wrong or bad. It's just that the model is not fit for these particular data, right? So if you had a bigger data set, the model would be fine. So it's only a problem where models meet data. And if you use a too complex model compared to the size of the data set you have, or you can say you have too poor data compared to the complexity of the model you require. And this is overfitting, actually. This is actually overfitting. And I mean, when P is bigger than N, you have sort of a super overfitting in a sense. Because then you have so complex model, you cannot even solve this here uniquely anymore. Okay, so how do we actually detect this if we have a data set? Okay, if you have P larger than N, you have detected it. But if P is smaller than N, we can still have this problem. So how do we detect it? Yeah, so if P is larger than N, you don't have to worry, or then you really have to worry but you don't have to worry about this question because then you can answer it right away. If P is smaller than N, first of all, look for pairwise correlations between the columns of X, right? If there are some columns here who are very correlated or exactly correlated or anti-correlated, I mean, it doesn't have to be a positive correlation. A negative correlation is equally bad, right? Remember linear combination, you can have if one predictor is -1 times another predictor. Yeah. Then so if you have exact correlations, you have this problem, or almost exact correlations, you're very close to this problem. What we can do and will do is to do a PCA. We saw that already in week 2, right? Do a PCA on this X matrix and inspect the variances. Because if you have P predictors, there must be P principal components with variances well above 0. If you don't have that, then you have this problem. All the principal or all the P, if you have P predictors, there should be P principal components with positive variances, you could say. And if some variances are 0 or as we will see, extremely close to 0, then you have this problem. Or if you don't have P principal components from the beginning, which is what is the case if you have P larger than N, because then you will have N principal components. Then you also have this problem. There is something called the variance inflation factors. I mention it here because we will see it briefly, but it's not a big thing, I would say. But this tells you how this can be used as a sort of a diagnostic tool if you have a model which has full rank, but you are suspecting you are close to losing the full rank. Then you can see it by these variance inflation factors. So what is it? It's actually the variance of the full model divided by the variance if you include only a single predictor. And if this is large, much larger than 1, it means that this single predictor is nearly linear, dependent with some other columns. So that particular predictor is perhaps a source of the problem then, right? So a perfect set of predictors, if you have really sort of well-designed experiments, they should be what we call orthogonal, and then all these inflation factors will be 1, which is the smallest value they can have actually. Right? They don't inflate variances at all. Right? No predictor inflates variances. So this, but in order to do this, you have to be able to fit the model, and that is not the case if you have if you completely lack full rank. You don't even get the fitted model, right? So, or yeah, but not the full model. You get something else. We will see. So this is only something you do if you are sort of having a fitted model and you are a little bit concerned that there might be some near lack of full variance, full rank. So let's move to R and have a look at how we can detect this problem. Lacking full rank. Let's have a look at this Audi data again that we have seen before. So let me just copy this code here, and I have made myself a script here now for week 7. And yeah, I should actually use my folder here as my working directory. So let's source this to load the data, load the tidyverse and so on, and then just fit the full model here now, like we have done before. Or actually we haven't done that before, because when we looked at this data last week, we didn't use all the data set, all the variables in the data set. We actually used, first of all, we took out this year variable. And we also took out these two factors. Notice there are two factors in here, transition and fuel. They are not numerical. Can you see that? Transition is manual or automatic transition, right? The gear system. And fuel is either G for gasoline or D for diesel. So there are two categories of cars according to the fuel and two categories of cars according to the transition. We have of course seen before that we can do regression also with factors included, right? So that's what I do now, ANCOVA, right? I include the factors as well. It's not really a problem. And I also include this one here. So now we really use all variables. Note how we write it in the code. You specify which is the response, and then you have this tilde operator, and then you just write a dot to say use the whole data set, or actually the rest of the data set then, right? Which is not the price. The price is the response here, first column. And then you specify the name and date. So let's run this like this, and we look at the summary output here. Here it is. And look, this looks fine except for here. Notice that this variable age, NA, this has not been fitted at all in the model. It has actually been eliminated or taken out of the model without us saying so. So what happened here? Is this sort of artificial intelligence, or what is it? Well, the problem here is that, and we will see that, we should look at the correlations. Let's look at the correlations between the predictive variables. And here's another trick you should learn. The model matrix function. So notice what I'm doing here. I use a function called model.matrix. And what does this do? It does part of the job that LM is doing. Notice I use, yeah, okay, I could have actually written it like this. I think price. I should do that instead. This was no, sorry. I use exactly the same formula as I did up here, but instead of fitting the whole model, I now only get the model matrix, the X matrix that you saw in the lecture, right? The predictor variables as a matrix here. Let's see if this works. Like this. And then we can inspect this matrix. And notice, this matrix now does not contain the price, because that was the response, right? That's the Y column from the lectures. It contains the other predictors plus the intercept, right? The intercept is also a part of the model, of course, right? And that's just a constant one here, column of ones. So this is a quick and easy and very nice way to sort of collect the predictors in a model. You specify the model in exactly the same way as before, but use model matrix instead of the full. So you can imagine that inside the LM machine, this is used to collect the X, and then these normal equations that you saw in the lectures are solved. But now we can actually inspect this matrix. So let's do that and look at the correlations here. So the correlations between the columns in the matrix, because that's what we want now, right? We want correlation between the columns here. You do that by the curve function in R. So that's straightforward. And then you get a matrix out with, yeah, let me run it again. So like this. So here we have then all the variables listed in the rows and in the columns. So an element here is the correlation between them. And of course, always you can see kilometers is always correlated with kilometers to 1, right? The best possible correlation, of course, because two variables, a variable is always sort of identical to itself. So all the diagonal elements will be 1 here. And this is of course symmetrical. So whatever value you have here, you have exactly the same value here. Notice that the intercept doesn't have a correlation other than with itself because it has no variance. In order to compute the correlation between two columns, both columns must have a variance. And the first column here is constant, right? It has no variance. So that's why it's NA all over the place here and also out here. But that's not so important for us because we are not really interested in the intercept. We are interested in all the others. And here we can now see that in most cases these are not particularly correlated, right? 0.45, this is super small, right? 0. Some are negatively correlated, minus 0.69, but that's not critical. But notice here. Here we have two off-diagonal elements who are minus 1. And that is year, right? Year versus age. They are perfectly anti-correlated. And if we actually plot these two against each other, one along x-axis and the other along the y-axis, then we see it. So this is actually the same information, I would say, in these two variables, year and age. Because you can see here, when age is 10, then year is 2007. So it means that this data set was collected in 2017. Because a car that was produced in 2007 then had an age 10 years old. And of course, as the years increase here, the newer the car, right, the smaller the age. So year and age is actually two ways of just measuring the same thing. And that is the reason for the output we got earlier, because now we have two perfectly correlated variables among our predictors, and actually this model matrix X does not have full rank. And what this LM function is doing then is just throwing out one of them, apparently, right? Because it fitted the model, but that would not be possible unless you remove one of these two from the model. So it just randomly skips one of them and uses the other one without telling us, I would say. So that's I would not have implemented the method like this. I would have instead issued a sort of a warning, or actually crashed the whole function and said you cannot fit the model with these two variables here because then you have no full rank anymore. You have to do something. Okay. What if we eliminate the variable ourselves? Of course, that should work fine. So now we fit, but without the age then, right? And we get exactly the fit that we are used to, right? And what we actually got before, because this was what LM did for us, sort of, without us asking for it actually, but yeah. So that's what we have to do. We have to try to fix this problem ourselves, I would say. So what happens if we now have this? So now we have full rank, right? Without this age variable or without the year variable. Doesn't matter which one we throw out. But let's try to now reduce the number of data cases, the n, right? So because now you saw that with the full this model matrix has 10 columns, and when we take one of them away, we are back to 9, right? So what if we have only 8 observations? What happens then if you try to fit the model? We have 8 observations. I subset the data matrix like this now, so I only use the first 8, but it doesn't matter which 8 I use. You can use any, it will be the same result. Because now n is equal to 8 and p is still 9, right? P is bigger than. So then LM, it doesn't crash, but look at the summary output. There is no computations here now for the standard error or anything. And these estimates here are completely sort of, yeah, who knows? What is this, right? So this is sure sign of a lack of full rank. If your output looks like this, then surely you have this problem. I must say I would have liked this LM function to give me some information rather than just trying to do the job and returning some nonsense output. But okay, that's the coding design problem. So how do we actually detect the problem? Let's use PCA, like I mentioned in the lectures. So we can take use PCA on this model matrix, and notice now I take out this intercept column because this will not be the principal it will not give us any information about principal components. It's a constant column, right? Any constant columns are just, you can just throw them away immediately because they will never contribute to anything with the principal components. I think you will even have some error from this precomp function if you include them. So that's why I throw out the intercept here. But then it leaves me with 9 columns, right? So let's see if we do PCA like this, and then I print this variance, explained variance, right, for each component. Let me print that. And now we can see here we have the variances, right? The biggest one in the first component, second biggest in the second component, and so on. And these are sort of big values. These are thousands, right? 10 to the power of 3. And then it drops to hundreds. And here we are down to smallish values, but it's still like 5, right? 1. Yeah, now it's 0.1. Now it's getting smaller. And notice the last one here. The last one here, this is 0. Because it's 10 to the minus 27, and it's only a rounding off error that makes this non-zero. So this is an indication, right, that we don't have full rank, right? Because we have 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 components, but the last one is not positive. It's actually 0. And that is because of this correlation that we saw. So let's just make a new model matrix for this reduced model. And again, I think I write price here. I don't know why you can do it both ways, but I think this looks a little bit better. So now I compute the model matrix again, but now I take out this h, right? So I have a x reduced here, like this, and you can see here this should now have 1 column less, yes. And again I compute the principal component without intercept, so now there should be 8 components, right? And if I look at the summary now, 6, 7, 8, there are 8, and even the last one is not close to 0. It's a smallish value, but it's not close to 0, I would say. So this fixed the problem. Now we have full rank. We can also do this reduction of the number of observations. And then I use the same reduced matrix, but I only look at the first 8 rows of it, right? And what happens then? Well, again, you can now see that the last, we still have actually eight principal components here, but the last one is again now 0. And now notice now p is equal to n because I took out the intercept, right? So we have n, we have 8 columns and 8 rows. If I go down to 7, then we have also only 7 principal components. Can you see that? And if you go down to 5 here, 5 observations, we have only 5 principal components. And the last one is 0 as well, so we actually have only 4 principal components who are. So the number of principal components is not always the same as the number of columns, it's the same as the minimum of number of columns and number of rows. And if you have this p larger than n type of data, then you will never have full rank because of this. So how can we deal with this problem where we lack the full rank? Well, we first assume that we cannot get more data because that would surely solve it, right? If you can get more data, that would be the best. But in most cases, we just can't get more data, right? We have the data we have. So then we have to reduce the model in one way or another. And last week we saw model sort of variable selection, right? And that is an obvious choice here as well. But an alternative is to do what we call compressing of the predictor space. And that is also something we will look into now. So variable selection we saw last week, the stepwise methods. And in this case, if you have p larger than n, you cannot do it backward elimination, right? Because then you start by fitting the full model. And this is no longer possible. So you have to only do forward selection in a sense. You have to start with nothing and then include variables one by one. So that's different, you could say. You can also do this best subset, but not all subsets, right? You can only do up to p variables, right? So not all the p variables. That's my point. So this is sort of tricky now, right? The stepwise forward is possible. It doesn't behave very well though in many cases because when you have super many variables to start out with, it's a little bit random which one is included in the first rounds, right? So stepwise methods are possible to do, but they are not. They will give sort of very random results in a sense when you have super many predictors to select from. And then we have the lasso methods that we will see a little bit more because the raw sort of plain lasso is also suffering a little bit from the same as this one here in this case. Then we have these compression methods that I mentioned above, and that's what we will actually look at now. Principal component regression, partial least square. So these are the two we will focus a little bit on now. And this, I think it's fair to say that especially this PLS method, which is sort of popular among many people at NMU, it's not that popular worldwide. Since we are at NMU, we should know a little bit about this method here simply because we are at NMU. Because this is so much used among some field of science that we cover. But in other fields of science, it's not used that much. Principal component regression is used quite a lot, I would say, in all cases. I would also like to go back to this variable selection and the lasso method with this elastic net solution, because I think this is a very good alternative for this type of problems. So these three we will focus on now for dealing with this problem. The PCR, the PLS, and the elastic net lasso, you could say. So first, the principal component regression. What is this? Well, remember from week 2 we talked about PCA, and then we say that the multivariate data variation we see in a data set, in a table, can be sort of split into a signal part and a noise part. And then we did PCA according to sort of this picture here, right? We have the full data table X here with P columns and N rows. And then we sort of look for a small number of principal components, Q, which we put into this score matrix here that we call Z, right? And notice this Q is much smaller than P. When we did the plotting, we only collected 2 columns, right? But let's say it's like 3, 4, 5 columns. If this is like 1,000 columns, this is much smaller, right? And then you have some noise here, right? The rest, you could say. So the principal component regression idea. Replace the original P predictors here, instead of using these in the model as predictors. Replace them with a much smaller value Q of principal component score variables. Here, use these as predictors instead of this. Because remember that these sort of captures most of the variation here. That's the idea. You lose very little when you replace these ones with this, and whatever you lose is noise, right? So that's good to lose that noise, right? We don't need noise in our models. So this is a natural sort of way of thinking, right? We know we have PCA. Why don't we use it here to sort of replace the original? And notice now we don't have a problem with this Q being larger than N, right? That's never the case, right? Q is always tiny compared to N, even if P is super big. So then we fit the model with this score matrix instead, you could say, or actually not the full score matrix, but only the first Q columns of it. So that's the main idea. So instead of the P regression coefficients here that belongs to each column up here, we now get some alternative regression coefficient, one for each column here. And I call them gamma here, just to give them a name. Because these are our sort of original regression coefficients. So this is different then. We change sort of from one coordinate system to another. The advantages of doing like this is that P may be now as large as it will, as long as we can use a smallish number of principal components Q. And the predictors we now get, the principal component scores, are orthogonal. So these variance inflation factors are as good as they can be, actually, 1.0. This is a sort of a perfect design. The disadvantages is of course that we now have very indirect relation between the response and the original variables. You have a direct relation between the response and the principal components, but the principal components are not the original predictor variable, right? They are some combination of them. So that's we lose sort of the interpretability here in this, but we will try to fix that later. We will see. And another problem is that we no longer have a strictly linear model due to this PCA step. So the theory behind the hypothesis testing and the F test and the T test and blah blah blah, this breaks down now. So that's a big disadvantage, you could say. We have fitted a model using the principal components, and we have the estimates for these regression coefficients here then, one for each principal component. Then we can compute the corresponding estimates for the original ones. So we can actually compute this from these direct in just like that, right? Because we have this loading matrix. So actually these the estimates of the original regression coefficients is the loading matrix times this new sort of the estimates for each principal component. like this. It's an inner product, this star. So this is how you. So this is will be then regression coefficient number I. And notice it's a combination of the regression coefficients that we get here. So you have to combine it for each row in this loading matrix. But this can be done sort of computationally, and is done. So remember that even if we don't even if we replace the original predictors with some principal component, we can still get estimates for the original regression coefficients as an output from this. But we cannot, but this assumption about distributions and so on breaks down, sadly. The partial least square regression, what is this? And this is very similar to PCR in some sense. In both cases, we replace the original variables with a set of rotated orthogonal components. And then in the PCR, we use the principal components. In PLS, we have some different types of components. So what are these? The criterion is different in the PLS compared to the PCA. So for the PLS components, find the directions having the maximum covariance between X and Y. And remember how we found the principal components in PCA. We only looked for the maximum variance in X. We never used the information from, we didn't have any response variable in week 2 when we did PCA. And that's the same here. When you do principal component regression, you do a PCA on the X only. But with PLS, you use both. That's the difference. You maximize covariance instead of variance. Apart from that, everything else is fairly similar. The next component is always orthogonal to all previous ones. That's the same for both PLS and PCR. And then you find directions maximizing covariance to Y. So that's really an advantage, I would say, in this setting here. The PLS has an advantage over PCA here because it uses this information about the response. Because in PCA, only X variable. No information from the response is used. So PLS is sort of bound to be at least as good as PCA, I would say. Because it uses this extra information that PCA doesn't use. But I also have to say that they typically come out pretty similar. It's quite rare to see a big difference between the results you get with PCR and PLS. They are sort of similar methods, and they also come out with sort of similar results. So in most cases, it's not critical which one of these you choose. But there are some peculiar cases where PLS will win clearly. It may also be some cases where PCR win over PLS, but I can't say I've really seen that. What I like to mention here is explorative use of PLS, because remember in week 2 when we talked about PCA, it was for exploring data. It was not for sort of doing some inference or finding significant effects on blah blah, right? It was just for exploring, looking at the data. The PLS can be used in a similar way in this case now. You need a response variable. You have to have that in order to use PLS. But you will also get loadings and scores, just like with PCA. And then you, of course, can plot your data using these loadings and scores, just as you did for PCA. So using the PLS loadings and the PLS scores is also a way to explore your data. So remember that. I think we will actually see that in an exercise. I think this is valuable to remember, that PLS can be used also in an explorative way, not just for sort of modeling the world. Let's have a look at how we actually do this in R. PCR and PLS. So let's do a manual PCR first. just to sort of make sure we understand completely what this is. So now I have this Audi data again from previous session, and let's look at this code here. Oops. Let me make some new space here. So I actually take that model matrix from previously where we had all the predictor variables, both year and age, right? And I take out the intercept now because that's what you do when you do principal components, right? Remember, we always center the variables when we do principal components. And then if you have a column which is constant, you center it, everything becomes 0, right? I also do the scaling here. And that is because this data, right, this Audi data, yeah, we have it here, they are measured in very different scales, right? So this is a situation where it typically makes sense to do this standardization of the variable, right? Because kilometers here and volume, these are completely different scales, right? So it's unfair to compare them unless they are standardized. So that's why I add that scale dot equals true to do the standardization. So let's do that and look at the summary of it, and then we can see here the cumulative proportion of variance. So it's like 43% is explained by the first one. If you include two components, we're up to 70% of the variance, and then it's like 84, right, and 92 and so on. And here we are 100% then. And we reach 100% before the last one because the last one is actually 0, right? We know that now, but we could have seen it here as well. So how many components to include here? Well, we choose q equals 2, it says here. I think I will actually try to choose q equals 3 now, just to do something different from what is in the text here. Let me copy this code. So what I do here, I now just make myself a new data table. I call it Audi2, where I take the original Audi, all the original variables, and I just add as new columns all the scores, right? Here. PCA object $x, that's the score matrix. So I add all the scores to this variable here. So if I do like this and inspect it, you will see this is the original data frame plus the PC scores, PC1, PC2, PC3, and so on. So now I have actually a super big matrix, but now I fit the model using price as response again, and I only use PC1, PC2, and let me also include PC3. Just to show you that you can have many here, right? Or at least you don't have to have two. When we plot, we always use 2, but here you can have 3, 4, 5, as long as it's not so many that you get this p bigger than n problem again. So q, or q then now. So now q equals 3, right? So let me fit the model and look at the summary, and then you have the output like you're used to, right? With effect of PC1, PC2, and PC3 here. And we can see actually PC3 wasn't significant, so it wasn't really a good idea to include it, perhaps. We should have stopped after 2 after all. Okay. But at least now I see that. So we can now compute these variance inflation factors, and let me show how to do that, because I mentioned it in the lectures. First of all, you need this R package called car, which has nothing to do with cars actually. The name, it has something to do with regression, right? What if we try to compute the variance inflation factor for this full model that we made initially up here? And if we try to run that, we get an error. We get an error because there are aliased coefficients in the model, right? So remember how it looked like, this full model that we fitted first. That was the one where you have both year and age, and one of them is sort of aliased with another one. They are correlated, right? And that this function actually tells us this now. You cannot compute variance inflation factors here because you don't have the full rank model. So that was actually a nice error message to get now, I would say. This should give an error message because it's senseless to compute variance inflation factors in this case. If we do it on the reduced model where we threw out the age variable, then we get some results. And then you can see these are now the variance inflation factors for each of the predicted variables. 2.5 here, 4.6 there, 1.7 here, and so on. And the smaller they are, the better, right? What you should look for here are critically big ones. I wouldn't say any one of these are particularly big ones. This is the biggest one, but this is not, I mean 9, 10, yeah, I wouldn't be too worried about that. What if we do on the PCR model that we just fitted? Look at this, look at this. This is as small as the variance inflation factors get. There are no variance inflation at all with this PCR model because the principal components are orthogonal to each other. There is absolutely no correlation of any kind here. The correlation is zero, exactly zero, between all the three principal components. So that's in some sense the best design you can ever have, which is a good thing with the PCR and the PLS actually. But I would say even this one here was not too bad. I have seen worse. Okay, so in reality we don't do PCR like this by doing first PCA and then fitting an LM model, even if you can do that. There is an R package called the PLS R package, where we have a function for doing this directly, and we typically would use that, I think. So you install the PLS package and you load it like this, and then we fit a PCR model with the function called PCR. And then you can see I specify here exactly in the same way as we are used to with the LM. The data is the Audi data, and scale equals true. Notice the scale is not without a dot here. In LM you write scale dot equals true. No, sorry, in principal comp up here. Scale dot equals true. This is scale without a dot equals true, but it means the same thing. So we do the standardization here. So we fit the PCR model like this, and this will now fit actually sort of models for 1, 2, 3, 4, all number of components actually, and give us. So if we have a look at this object here, we can do that. The PCR object. It's a list. And now, for instance, the coefficients here, what is this? It's now an array with 3 dimensions. So if I try to plot it out or print it out here, it's called PCR ob dollar coefficients, like this. Yeah, you can see that these are now the regression coefficients, but they come again and again and again, because this is the regression coefficients you get if you use PCR with one component, right? And then if you use PCR with 2 components, you get these regression coefficients. And with 3 components, these coefficients, right? They change depending on how many components you now use. So that's why it's stored in sort of a 3-dimensional array, 9 times 1 times 9, because there are 9 components to choose here, right? And you can see the same for the scores and the loadings and so on. The scores is the same as we are used to actually. It's a matrix, right? Because it's if I type view here, let's hope this will work. No, that's true. The scores matrix is not really a matrix. We will see that later. It's a sad thing, this, because the people who made this package, it's actually a Norwegian guy, decided to not make these scores and loadings into proper matrices. So when you make use of them, you have to convert them to a matrix. But it's actually the same score matrix as we find in PCA and the loading matrix as we find in PCA. But they are stored in slightly different values. Yeah. Fitted values, yeah, they are also again now one for each. Here you can see. This is also one for each number of components now. 30 times 1 times 9, the fitted values. So that will be similar to the regression coefficient that you saw here. So now we can actually make some plots here. Let me copy this code. Familiar plots, I would say, based on the content of this PCR object. We can now make PCA plots, and both loading and scores actually. So let's do the loading plot here. And the reason I need this Magritte package is this super silly thing that the loading matrix we extract from this PCR object is not really a matrix, so we have to convert it to a matrix like this. And this is because of the implementation. Yeah. Let me load the Magritte package. And then I can collect the loading matrix. And then I think this code here is more or less like we did when we did PCA plotting. And we can sort of recognize the plot from week 2, where we did PCA 1, PCA 2, right? You have the origin in here, and we can now see that, first of all, we can see that age is completely anti-correlated with year, because they are going completely opposite directions from the origin here. So these are sort of 100% anti-correlated. And actually the same with volume and CO2 is also almost, I think it's a tiny little angle here, but they are also very, very anti-correlated, it looks like. And we can see that along PC1 we have the biggest loadings for age and year then, because they will sort of have the same loading in each direction, right? And weight. Yeah, and the similar fuel is an important variable for the second principal component. So this is exactly the same loading plot as we would get if we did PCA on this X matrix only, in fact. So, and you can do the same with the score plots here. Let's look at the PLS then. So how do we do PLS? This is the code for it. It's the same PLSR package, and the function is called PLSR for PLS regression. But you can see everything else is the same as for the PCR above. And again, we can make this loading plot based on the PLS loadings now. And this will now be slightly different from the previous plot because it's no longer the principal components. It's the PLS components. And the code is very similar though. And here you can see the picture now. You can see it's not super different from the previous one, right? Because again, we have age and year on sort of opposite of each other, volume and CO2 opposite of each other. Yeah. So, but they are positioned slightly differently, right? And now you can see age and year is completely along PLS component 1. So they are clearly the most important variables here for the response price, right? Because they are along the first principal, first PLS component. Yeah. You can also make a score plot in a similar way. And that's often nice to do because now we get an impression of how these variables can, if there are some pattern, right, in the variables. And now I used actually the response variable for coloring the dots, right? I used the response as a coloring of the dots. And now we can clearly see here from this score plot. Now each dot is a row, right? A car in our data set. Now we can clearly see that on the right hand side we have the expensive cars, typically the high prices, right? Brighter blue. And on the left side we have the cheap cars. That's sort of the main gradient, right? The gradient in it. It goes from dark to light when we go from left to right here. And then if we go back to the loading plot, right? Then we can see that, okay, in that same direction we have this year and age. So it means that, of course, the expensive cars over here, they have a large value for year, or a small value for age, which is the same thing, right? They are new cars, right? If you have a large value for year, it means it's a recently made car, right? Or the age is small. So that makes sense. The main explanation for the price of car is how old it is, actually. That's what these two pictures tell me immediately. Okay. So we have seen that we can use PCR and PLS to fit a model to a smallish number of components. But how small is this value Q? How many components should we use? We saw that both the PCR and the PLSR function will output sort of the results for fitting all kinds of models, right? From Q equals 1, 2, 3, and so on. So which one should we choose? What is the proper compression of our data? Well, we could of course look at the scree plot for the PCR, right? PCA scree plot. But in reality, that's not how we do it. We use a minimized prediction error. That's what everyone does. And the point is that if you choose a too small Q, we include too little signal, and we get poor predictions because of underfitting. If you have the optimal choice, you include most of the signal but little of the noise, and you get best possible predictions. And again, if you then use too large Q, we include the signal, okay, but also a lot of noise, and then we get poorish predictions again due to overfitting this time. So it's the same sort of problem that we saw last week as well. But instead of including fewer or more predictors, we now include fewer or more components. It's the same, but it's the same problem. So again, we use cross-validation like we saw last week when we used the lasso in order to find how much shrinkage we should use. Now we use it again to find the proper Q value instead. And the idea is of course the same as before. Set aside a smallish subset of the data cases as a test set, right? Some rows of your data set are set aside, and then you fit your model to the remaining part, the training set, and then you predict the response of the test set using the predictors of the test set. But notice these were not included in the model fitting. That's important, right? And then you get some predicting value here, and then you can actually compare y-test and y-test hat to see how close you got. And then you repeat this again with a different test set, right? Different part of the data being set aside. So we saw this in detail in last week. It's the same idea. And then we compare these two in the end. And how do we compare them? We saw last week this MSE. This is just the square root. It's called RMSEP. I mean, these criteria are more or less the same. They come up with different acronyms. Root mean square error or prediction, right? But we saw last week we called it just MSE when it had no square root. Actually, I wrote it here. That's what we saw last week, and this is, you can see it's the same thing without the square root. Yeah, it doesn't matter if you take this, everything is just scaled up or down. The minimum is the same, right? If this one has the minimum for Q equals 3, This one will also have the minimum for q equals 3. So this square root or not square root, it doesn't make any difference at all. Whoops. So fit the models of all complexity, right, from q equals 1, 2, 3 and up as large as you like. And then you do this cross-validation for each one of them. Fit model to training data, predict test data, compute this MSE for each Q value. And exact the same procedure will do for PLS as you do for PCR. There is no difference here. It's a different fitting machinery. But the cross-validation procedure is the same. And the Q value given, then the smallest RMSEP or MSE or whatever you like to call it, is then the optimal one. And then remember here, and that was my drawing here. Remember this drawing we saw, we have seen it before. If you have the sort of model complexity here, which is now the number of components, the Q instead of the P, and then you have this error up here, then it will typically be something like this. It will start out with bigger errors, and then it will drop, and then there will reach some minimum somewhere in here, the smallest possible, right? Q, and then it will start to grow again. So you have underfitting and overfitting over here. And then the optimal Q is okay, the minimum, but remember this, right? There are always many, or almost always, there will be many different models here who are almost equally good. So we shouldn't sort of be too fixed on selecting one particular one here. We could be a little bit flexible inside here, but we should not go out here or out here. Right? So this is again eliminating the worst cases, but we are still stuck with a number of cases here that we could choose. So please remember this. Don't be sort of too over-fixed on finding the minimum here. Let's have an R session where we do this cross-validation and see how this turns out. PLS and PCR with cross-validation. So let's see how we can do this with these built-in functions in the PLS package. And the first thing we will do is what's called leave one out cross-validation. What does it mean? It means that you use the smallest possible test set ever, which means one single data case. So you set aside one single data case in each iteration, right? You iterate through your data set, and the smallest possible test set is one single row. And that's leave one out, or LOO, as it's short. So here is the code for doing that. And notice now I use PLS, but it's the same for the PCR function actually. So what is different from the previous one? This is the same, this is the same, this is the same. And here you add then validation equals LOO as a text, leave one out. And now I will fit the model again, and we can look at the summary of the output, and then we will have some kind of perhaps I should do it again like this. Yeah. And then you can see it outputs some RMSEP values from the cross-validation. So if you include only the intercept, actually no predictors at all, this is the cross-validated error or RMSE value, 83 point something. Is this big or small? Well, I don't know. This will depend on your response variable, right? So it's not the absolute value we are looking for. We are looking for instead now how it changes. So if you include one component, PLS, it drops dramatically from 83 to 37, right? So remember that curve that I showed in the lecture, right? It typically start out with a biggish error, then it starts dropping. Because here we underfit severely, right? Then it starts to improve. If we go to two components, it gets even better, but not now. You can see the improvement is very small. It drops only from 37.27 to 36. Yeah. And now if you go to 3 component, it starts to rise again. And then it typically rises the more and more the further out you go. So now you start overfitting, right? This is overfitting here. And it can rise to super big values towards the end, but it was not super big here. But we can clearly see 2 component was the minimum, but we also see, okay, 1 component is almost as good as 2 components, right? And 3 is also not that much. So it's somewhere around here. We should stop, right? 1, 2, 3 components. So that's, and actually when we made this plot, we plotted 2 components, right? Because that's what we can plot. So this time it looks like that was actually also the optimal choice of Q, 2. So that was lucky, you could say. We can, instead of doing this leave one out cross-validation, we can do k-fold cross-validation like we saw last week when we used the lasso. Because this leave one out cross-validation is a little bit, I would say, it has a tendency to choose the Q value slightly too big. Slightly too big. It favors overfitting a little bit more than underfitting. So, and why is that? Because you take out only one single observation at a time. So the training set you are left with lacks only one of the observations. And that means all the training sets become very, very similar to each other. There's a small difference between all the training sets. And that makes this a little bit, it has a tendency of choosing Q a little bit too large, I would say. So what we can do instead is to use a test set of any size that we choose, right? Instead of leaving out one, we can leave out bigger test sets. So then the code would look like this. You can see it's the same up to here. But instead of saying validation equal loo, there is only one way to leave one out. But if you say validation is CV for cross-validation, and then you say segments equal 10, then you will split your data set into 10 subsets. 10 subsets, right? And this is exactly what we call 10-fold cross-validation, right? So when I write k-fold here, it means you put in a value for the k, right? So in this example, it would be 10-fold cross-validation. And this value you choose yourself, right? But typically 10 is a very typical value, or something around that size. Because now you split your dataset into 10, and this was 30 rows, right? This dataset has 30 rows, so it means 3 rows in each test set. And you can even go down, of course, like 5, but no smaller than 2, of course. Right? Because then you don't do cross-validation at all. It has to be 1 test set and 1 training set, right? But let's stick to 10 then. The problem, or what you should remember now, is that this PLSR function will now choose randomly which rows are in each segment or in each test set. And that is, for that reason, the result you get when you run this code will not be exactly the same each time you run it, because there's an element of randomness in. So let's run it and see. We can run this exact same as we did before. Yeah, let me look at only the summary here. Yeah, so let's look at the CV now, the RMSAP. And we can see the values are sort of similar, right, to the one we had got with the loo. And here we have a minimum, yeah, and then it starts to climb. So actually this time it was exactly the same outcome. We would choose Q equals 2 again. But I mean, if you repeat this many times, and notice now, now still 2 was the minimum here, but the values changed a little bit, right? So if you do this many times, you will sometimes see that the minimum can fall on the neighboring components, right? And again, the minimum was here at 2. So this is obviously the best, but due to this randomness, you could stumble across cases where this one was the smallest or this one. Please remember that. Due to the random selection of which segments, which data cases belong together in a segment. But anyway, I would choose this k-fold cross-validation, I think, over the LU. And here I make a plot of this press values, as we call them. Yeah, and that's what is the press value? It's actually these RMSE values that are output here are not actually the ones who are stored inside this PLS object. If you inspect the PLS object here, you will not find RMSE inside here. But if you look at the there is something called oh, sorry, this was the wrong object. PLS tenfold, this one here. Yeah, there should be something called validation. Here it is, validation inside that object. And here you find something called press and press 0. It's not RMSE, but here you can see my conversion. No, here I plot the press values directly. Well, in an exercise we will do the conversion, so you can see they are again just a different way of expressing the same thing. This is also prediction error. So if I plot this one, we get this picture here, right? That's the same as we saw in the values. So it's quite typical to make a plot like this to show where you have the minimum. So here we can see the minimum is at Q equals 2. And then it starts growing again. But even at one component, it's not super bad. So we could perhaps even have stopped here. Yeah, so this corresponds to the curve of how error develops when you go from underfitting to optimal to overfitting. And sometimes the optimum is very close for very small Q values. Sometimes you have to choose quite many. This depends on the data. So how about the significant effects? Because we have now seen how we can fit PCR or PLS models, but we get regression coefficients. But how do we know which ones are significant, right? So we start out with P predictor variables in our X, but we end up doing the regression on the Q predictors in Z. But these are the ones we are interested in. I mean, we want to know which ones of these variables have an effect on our response. The fact that we do this sort of compression step here to solve a sort of a technical problem doesn't change the problem from the start. We want to say something about these predictors. We have no sort of interpretation of these components. They are combinations of everything, right? So for prediction purpose, we could stop here and don't think about this problem. But since we are not so focused on prediction, but rather on explanation, we would like to take our sort of results back to the original variables in some way. The original variables we are concerned about. So how do we do that? Well, first of all, we have seen previously that we can actually compute the coefficients for the original variable. We can compute their estimates, right? But we also said that okay, but the distribution, right? The normal distribution and the theory that we have used for the errors of this estimate, we can no longer use to make t-tests like we did before, because it's no longer a linear model due to this PCA or PLS step. So this becomes now questionable. We don't have, well, there is no maximum likelihood anymore of this. The fitting doesn't sort of maximize the likelihood function, because how does the likelihood function look like even, right? That's regardless of the distribution of the errors. The standard errors are difficult because what are the degrees of freedom here? That's also a difficult issue. And the normal distributed errors is no guarantee that we will have t-distributed test statistics anymore, like it is when you have a pure linear model. Then this normal distribution here results in a t-distribution over here. But this is no longer guaranteed. So how on earth do we make some sort of significance statements? Is this significantly different from 0 or not, right? This estimate we get. And then I think there are actually some ways around this, more or less good. But now I take this opportunity here to introduce the bootstrap idea. And I should mention now immediately that bootstrapping is not something which is specifically related to PCR or PLS or anything. Bootstrapping is a completely general idea. And the only reason I use it here because this was an occasion where we could sort of argue for it. Because everything else breaks down, what do we do when all else fail? Then we turn our attention to methods like bootstrapping. And what is the main idea? The current dataset we should always look upon as a sample from a population of datasets, right? Whenever you have collected some data, you should always think that, okay, I collected this dataset, but I could have collected many other datasets, right? If I just repeated this. And then, of course, what we try to do when we do all this hypothesis testing and stuff is to make our statements valid for the entire population of datasets, not only the current dataset. We have stressed this before. So, what we do now, we can imagine we have several new datasets from this population, and we just fit the model repeatedly using the same approach to each one of them. And then we observe how this estimates varies from dataset to dataset. That's how variance comes into the estimates, right? Because datasets vary. Of course, we don't have all these new datasets. So how do we sort of obtain this information then? And here is the bootstrapping idea. Form our new bootstrap datasets simply by resampling with replacement the original data cases. So you sort of create sort of artificial datasets by resampling with replacement the original data cases. And what does this mean? It means that if you had like 10 data cases originally, 1, 2, 3 up to 10 rows, right? You now make a new data set also having 10 rows where you sample the rows from the original one with replacement. So it means you can sample row number 1 and you can sample it again. So the new data set will contain the original rows, but some of the rows will be multiple times and some will not be there at all. And some will be once, some twice perhaps, right? And some 0 times. So the new dataset will not be a copy of the original one. It will be a slightly different dataset. We call it a bootstrap dataset. And then we fit the model to this new dataset in exactly the same way as we did to the original one. And this we can do now over and over and over and again. So we make use of computing power. Computing power. And this takes a lot of computations. But it has turned out to be a useful approach for dealing with these cases where everything else sort of breaks down. Of course, almost needless to say, these bootstrap datasets are not as informative as real new datasets would have been. Of course not, because we just reuse our old data. But it can be shown that they are actually of some real value. We can actually, from this procedure, come up with some sensible estimates of variation. And this will in principle work on all kinds of models and all kinds of data, this procedure, and that's the real strength of it. And that's why we should know about this bootstrapping way, because sometimes for some reason we have models or we have data that doesn't sort of fit into this, all these assumptions of the linear models and so on. And then we can resort to this procedure here as a sort of, as a way of at least make some inference about our results. It's not as good as if it was completely according to the theory, but it's usually good enough. So it's not like you can replace the classical theory with just doing bootstrapping, because it doesn't have the same sort of power. But it's nice to know, and its power is sufficient for being useful, I would say, in many cases. In many cases. Especially if the alternative is to not do anything. This is much, much better. So, how do we do now? Instead of doing hypothesis testing and p-values, we typically make confidence intervals for the parameters. And then we see if this confidence interval cover, in this case, 0, right? If the slopes, if the regression coefficients, they are all slopes, right? If they are covering 0 or not. That's what we are asking ourselves. So can we make confidence intervals? Then we have the same, then we can make sort of statements about significance, right? So assume we have fitted now a model to this data, and we have seen how to do that. Then we form capital R bootstrap samples by this replacement, sampling with replacement. And all of them must be exactly the same size as the original one. So they can just replace the original dataset. And then we fit the model to each of them, and we collect the regression coefficients in each case. And now we have to do that for each value of Q, or we have to select a value of Q, right? We have made a decision of that based on cross-validation, for instance. Now, and then we can compute 100. Yeah, this is just, for instance, a 95% confidence interval. If this is 0.05, right? 95% confidence interval for the regression coefficients, and if it doesn't cover 0, it indicates a significant effect at the 5% level. There are several ways to compute these confidence intervals, and what we will see now in this example I show you is called a BCA, bootstrap confidence interval, bias corrected and accelerated bootstrap confidence interval. And I will not dig into the details on how different bootstrap intervals can be computed. We will just stick to this one now in this example here and in this course actually. So it actually tries to correct for some bias and skewness due to this bootstrap sampling, because it obviously creates some, these bootstrap samples are slightly different from sort of real data, right? So that's what we are trying to correct here. There are some nice books about bootstrapping, so if this is something you feel that you should know more about, these are 2 books you could look out for. I think that bootstrapping is a very nice to know technique, because it can be used everywhere, and sometimes we don't have any other solution, I would say. So I think bootstrapping is really worth looking into. And I should also say, I think that it also improves our understanding of the whole uncertainty. But that's a different thing. Let's turn to R again and see how we do bootstrapping now to compute the confidence intervals when we have done PLS or PCR. Let us have a look at using bootstrapping to compute the confidence intervals for the regression coefficients when we use PLS or PCR. And I do it for PLS here, but the procedure will be exactly the same for PCR, and it wouldn't be very different for any other fitting method as well. So first of all, you need to have the R package called boot. We will make use of that. And inside this R package, there is a function called boot that do this bootstrapping hard work for us. But in order to use this boot function, we need to supply it some input that it always requires. First of all, of course, the data set that we will bootstrap, and that is pretty obvious. What is not so obvious is that it also needs a function. It needs a function that where we sort of indicate how the model fitting should be done. So let's start by making this function actually. And that is what I do up here. So let me copy this code here and let me explain a little bit what this is doing. So imagine now you're going to do bootstrapping and you want to fit, for instance, a PLS model over and over again to slightly new data sets. And this function will help us in doing that. So what is the input? What is the argument to this function? First of all, a data table containing the full data set. And here I call it data TBL because this function should be used within a data set, right? So the name here has nothing to do with the actual name of the data set. This is just a local name of it, right? The second argument is a vector, and this contains now row numbers. Row numbers, which rows from the original data set should be used for each bootstrap dataset. So you can see inside here we do exactly this. We take the original data table and then we select just these rows indicated by this vector here, right? And notice now that this one contains now row numbers, and the same row number can be occurring multiple times, while some other row numbers are not there at all. So imagine this had like 5 rows, just as a small example. The full data table, the full data table has 5 rows. And then this one will also contain 5 numbers, but it will not be 1, 2, 3, 4, 5, because then this data set here will be just a copy of the original one. That's not the point. It should be different from the original one. So this vector will then, for instance, contain the numbers 1, 3, 2, 1, 5, for instance. Meaning that row number 1 is sampled 2 times, while row number 4 is never sampled at all. So this one will be slightly different from the original one. This here on the left hand side. So this vector here is actually sort of given to this function in each of the bootstrap runs, right? A new vector here. So this will be the same each time. This one varies each time to make this bootstrap sample slightly different for each time this function is used. And then the rest of this function here is the code that I choose. How do I fit the model, and what parameter, what coefficients or whatever from that fitted model is it that I want to compute confidence intervals for. So now you can see here I use PLSR, I use price as response, and I use this bootstrap sample as data. That's really important, right? That the data you use here must now be this bootstrap sample, not the original one, because then everything is pointless, because then you fit the same model on exactly the same data over and over and over again. You get exactly the same result each time. So that's no point. The point is to use this bootstrap data now. That is slightly different from time to time. And of course I do the scaling. I put the number of components here. And let me just mention, why do I do that? Because this is now the upper limit for how many components I choose. Uh, Notice the number of components is an input argument here. How many components model do you want to use? And down here we use that to pick exactly, for instance, let's say this was 3 then, right? Then we want the 3 component model from PLS and the regression coefficients from that. This is what we want to study now, make confidence intervals for. And if so, if we fix this one to 3, it comes as an input here. We could have typed it directly in here, but then the function will not be useful for any other choices. So I want to have it as an argument, right? So I can use the same function whether I choose 1, 2, 3, 10, 100 components. The function should be the same. And then I put it here as well, just to save time. Just to save time, because PLS will take some time, right? And if you have a super big data set, it tries to fit models for 1, 2, 3, 4, up to maximum number of components, and this can take some time. If I know I will never use more than, let's say, 3 components, it's no point in going further than 3. So it will save me some time by putting this here. Okay. But notice here now, if you want to do a PCR regression, you just simply replace PLS with PCR here. Perhaps you change the name of the object here and here as well. Or you could use the LM function even, right? Or any other method for fitting a model here. So you have to change, by changing this function, you control how your model fitting is done. That's the whole point. And then you return the coefficients, because those are the ones we want to have confidence interval for. Notice you could have returned other aspects of this object if you want to compute confidence interval for those. Bootstrapping is completely very general, right? So let me copy the rest of the code just to show how we use this function now. So first of all, I have to run this to, or source it as we say, to make the function available to us. Now it's a function here that is ready to use. Then I load the bootstrapping package, and now I fix the number of components here. Based on the cross-validation we saw previously, it looked like 2 components was a good idea, so now I say use 2 components all over. And here is the bootstrapping now. I use this boot function from the boots package. I supply to it, first of all, the original dataset from which we are going to do sampling. Then this function that I made up here that do the model fitting for us, and also actually this extracts the subsample and do the model fitting. Then I have to specify how many bootstrap samples do you want. And when you compute confidence intervals, you should typically use 1000 bootstrap samples. Don't use less than this. 1000 samples. This may take some time, but that's the price you have to pay for doing bootstrapping. Computing power or computing time. It could be a good idea though to try with only 10 the first time, just to check that the code works, right? Because then you don't have to sit around and wait forever for the result. But as soon as you see that the code is working, use 1000 here when you do confidence interval. Yeah, and then we supply this last information, which is just passed on to this function here. So let's run the bootstrapping here now, and you can see it works, but it didn't take very long time. And that's because our data set is so small, so even 1000 bootstrap samples took just a few seconds. Let's inspect this object now. What does it contain? It contains a lot, but this is the important one, the T here, the test statistic. Notice it's now a matrix with 1000 rows and 9 columns. Let's have a look at it. I make my window a little bit bigger here to inspect it, and it's this one. Yeah, let me scroll back to the top here. So Each row in this matrix is now contain the estimated regression coefficients for one bootstrap sample. So this is now for the first, this is beta 1 estimate, right? This is beta 2 estimate, beta 3, and so on for one bootstrap sample. And now the next row is then the same, but for the next bootstrap sample and for the next bootstrap sample. So actually for beta 1, the values down the column here now are the different estimates we get for the slightly different bootstrap sample. And this gives us now the impression of how this estimate varies, right? But we can see they are all around like minus 20, plus minus a little bit. So from this information, we can now make a confidence interval for this regression coefficient. And the same for this one, and for this one, and for this one, right? And that is exactly what we do now in the rest of this code here. So here I make myself just a matrix with zeros where I want to put these results. And then I put some row and column names just to make it more easy to understand what it contains. Like this. Then I put in as the first column here the actual point estimates. I mean the estimates of the regression coefficients that I got using all the data, right? The first PLS model we made, and with same this many components. So I fill in here now. So if you look at the CIMAT now, it contains the point estimates for the regression coefficients, but it's still zeros out here. And now I want to fill in the lower and upper confidence interval limits, right? We can see it's on average like minus 20 here, but what is the lower and upper confidence interval limits for this regression coefficient? And that is exactly what I do here now with the for loop. And you can see inside here I use this function called bootCI, bootstrap confidence interval, where I need to supply this boot object that I got from up here. I need to specify the level of confidence, 95% here, 0.95. You can change this if you want different values. And here is the type of confidence interval, because it's this can be computed in several ways. So this is the BCA type of confidence intervals that we will stick to here. Yeah, and then this is for component number I. No, so regression coefficient number I. So I do this for each regression coefficient. But it's not that many of them, so here it is after we filled it in. So now you can see the point estimate for this first regression coefficient for kilometers, minus 20, the lower. Before we conclude this session, let me say a few words about variable selection using the elastic net. Because PLS and PCR don't really select variables, right? They just compress the original predictor space to a different and smaller dimensional space, and then do the regression there. Variable selection is also always a possibility for avoiding this p larger than n type of problem. And last week we saw this lasso method, where we used that for variable selection. We may use lasso even if p is larger than n. Technically it will work, you could say, but it has some it turns out it's not the perfect method, because if we have correlated predictors, and that is the problem, right? When we have a situation like this, we would actually like to select these together. Why? Well, try to remember back to this talk about the confounders that I mentioned in week 6, in the causal inference type of idea. you can have confounders, right? You have two predictors where actually one of them is the real cause of the response, while the other one is just correlated, and it looks like it is the cause of the response. Remember this example with the number of mosquitoes and tourists, right? And and the temperature, which is actually the real reason for this covariation. If you have a situation like this, you would like these correlated variables to be both either selected or both deselected, because they should sort of travel together. Because otherwise, if your selection method starts to throw out one of them at the expense of the other, you may throw out the wrong one, and you are not seeing the real cause anymore, right? You only get the confounding effect. So whenever you have this situation, they should be selected together. And this is the problem with the original lasso, and also the problem with the stepwise methods that we saw last week. They will typically select one of these correlated variables and leave out the other one, and never tell you that these were correlated. So that's a bad thing. How can we fix this? Well, yeah, both the stepwise and the lasso tend to select one but not the others, and that's dangerous, right? Because then the ones you don't select may be the actual ones you should have seen. The elastic net extension to lasso is a way to fix this. And what is it? Well, here I will show you this criteria, or how the method is working. Select now values for these regression coefficients such that this horrible thing is minimized. And notice this looks a little bit like lasso that we saw last week, but let me point out the difference. And there are two parameters here, lambda and alpha now, because in the lasso there was only the lambda. And if you look back at the previous week's slide, you will find that everything here and up to here is the same as the lasso, with the exception that this alpha was not part of it. Alpha was 1, you could say. But this term here is the lasso extra term to the least square solution. Now we add another term here, and notice the difference. Here we have absolute values, or you could say it's Manhattan distances from the origin, while these are squared values. So these are actually Euclidean distances from the origin, but it's the same regression coefficients. So we have both sort of a first order term and a second order term. And what is the idea here? If you set alpha equal to 1 now, then you can see that this becomes 0. So this extra term here vanishes completely. And then we are back to the original lasso with alpha equals 1 here, right? So in the elastic net, if you set alpha equal 1, it's a pure lasso again. However, if you do the complete opposite and set alpha to 0, then this term vanishes, right? The first order term vanishes, and then this one becomes 1. So you only have this square term, and this is actually called a ridge regression shrinkage. It has a name. So you can say that the elastic net is sort of a combination between a pure lasso method and a pure ridge regression method. The point is the ridge regression does not select variables. It turns out that with this criterion here, none of the betas become 0. Ever. They can be small but not 0. You have to have this first order term to get that 0 values, to select, to deselect something, to throw some variables out. Ridge regression will never throw a variable out. It will just shrink them, more or less. But by choosing now an alpha between 0 and 1, we can get sort of a little bit of both. We can do shrinkage and selection at the same time. And it turns out with this second order term added to the lasso, the variables who are correlated will now tend to be selected together. So that's the whole reason for doing this, adding this second order term here. To make sure that variables who are correlated are also selected or deselected together. So as I said, ridge regression means shrinkage but not selection. All variables are used, and this is just the same as with PCR and PLS actually. So you can actually think of ridge regression as sort of a compression method as well, because it doesn't throw out anything. It uses all the variables, just like PLS and PCR. Remember, the principal components are always combinations of all the original variables. The same for the PLS component. Always combinations of all the original variables. Nothing is sort of thrown out until we start looking for significance, right? The same with ridge. But since we now combine ridge and lasso, we do throw something out. So we should use alpha somewhere between 0 and 1 in order to get a more modest selection, but correlated variables will now tend to be selected together. And exactly which value should we choose? Well, this is not something we can say directly. You have to adjust this by a dataset. But try 0.5 then as a first choice, right? Right in the middle of the extremes. That's where I would start. Let's go and look into R and see how simple it is to do this elastic net in R. So let's see how we fit an elastic net model and use it for variable selection, even when we have p larger than n, or if we have some correlated variables. And that's exactly what we have in this small Audi dataset. You will look at some bigger datasets in the exercises where we have p bigger than n, much bigger than n actually. But let me copy this code here now and explain how it works. So first of all, we use this GLMNet package again that we used last week for lasso. And if you remember, we used actually this same function here last week as well, CVGLMNet. So this code is almost identical to what we did last week when we did the lasso. And now and remember, we couldn't use that formula way of specifying the model, so we have to put the response as a separate vector. I call it y for obvious reasons, and then the model matrix also as a separate entity. And again, yeah, okay. Here is how you construct a model matrix from all variables, also including the response, and that's why I take minus price. Or I could have done as I did previously, right? With putting the price as a response here. Doesn't make any difference. It will be the same model matrix. So let me do that. Y. Yeah, first let me load the GLMNet package. Put y as a separate column and x as a separate matrix here. Yeah. So now I have the same again, right? With the intercept and everything. And then I used the CV GLMNet in the same way as we did last week with X and Y. I used tenfold cross-validation. This I didn't mention last week. Standardize equals true. I mean, in this case where we have this data set here with different scales, we should standardize, right? And we did that when we did PLS and PCR, and we should also do it for lasso or elastic net. However, we didn't do it last week, so did that turn out completely wrong? No, because actually standardization is default on here. So actually you don't have to specify that you want to standardize, because that is by default always done. You can specify that you turn it off. like this, right? Standardize equals false if you don't want to standardize. But by default, the GLM methods will always standardize unless you tell them not to. So I can actually wipe it out like I did now. And then we have to set this alpha value here. And that's the difference from what we did last week, because now we use the elastic net instead of lasso. So if you don't specify this one, it means it's set equal to 1. So you have the pure lasso solution. But now we don't want the pure lasso solution. And then we lower this alpha value somewhere between 0 and 1. And 1/2 is a good first guess. So let's see what's done here, and then I fit this. And now the cross-validation is done in order to find this shrinkage, right? If you remember from last week, we can make this plot. And it looks similar to what we saw last week. So now we can see here you have the mean square error, MSE, and the various degrees of shrinkage, the lambda here. And now it looks like this. We have a minimum over here, but it's fairly flat, right? So this is the sort of best shrinkage, and then you can see it selects like 6 variables out of the 9. 6 variables. But you can go down here and have an error which is not significantly poorer than the minimum, and you have only 5 variables. So, so this is very similar, almost identical to what we did last week. Yeah, I mentioned it. So actually, what happens now if we change this value here of alpha? Let me put it back to 1.0. And then we get exactly the lasso as we did last week. So let me run that and make the plot. It didn't change very much. What if I set it to 0 then? The other extreme. And run it. And then it changes quite a lot. And notice here, all variables are used. There is no elimination of anything. And the shrinkage minimum changes, right? So this is now a pure ridge regression. No variable selection at all. So this is sort of pointless from our point of view because we want some variable selection, right? So we need to put some value here. So let me go back to the 0.5 value again. I'm not sure if 0.5 is optimal here, but that will at least give me some selection, right? Some reduction from 9 to 6 or even 5 variables here. What I want to do now as a last sort of session here is to use bootstrapping again, but in a slightly different way from what we did previously. When you look at this plot here, we see that around the minimum here, everything is kind of flat, right? So it's a little bit random. We can now imagine if we replaced our current data set with a slightly different data set, this minimum here will jump to the left or right here a little bit. And that means some of the variables we selected now may not be selected, or some other ones will be selected if we change the data set slightly, since it's so flat here, right? And that is exactly what we do with bootstrapping, right? We try to construct new data sets who are slightly different from the current data set, and then we look at how things vary. And what I would like to look at now is I would not like to have a confidence interval for anything, but I want to see how often are the different variables selected if I change my data set slightly. If you remember from last week, we took a sort of all the models in this range here between the minimum and this first standard error. And we sort of took a vote across all the models here to see which variables are frequently selected and not so frequently selected. So what I want to do now is to do this slightly better, I would say. Instead of averaging across these here for one particular data set, I instead only look at the minimum, but I look at the minimum for many different data sets. And then I take the votes over all these data sets instead. And that is exactly what I do here. So now I need to make this function again, right, that we saw previously when we computed the confidence intervals for regression coefficients. I need to make a similar function because I'm going to do bootstrapping again. Again, I need this data, the full data set, and this index here, right? Or this vector to select the rows. And here, so this is the thing. Actually, this one I can throw away now. This is some leftover from the previous code. I don't need PLS. I'm not going to use PLS here. But this I need. These two must always be there. And then the third parameter I call alpha now, which is obviously the alpha in ElasticNet, right? And now I use ElasticNet with tenfold cross-validation here. First, I make the data sets like we know we have to do with ElasticNet. And notice here, I use this bootstrap sample, right, that I create up here. The first thing I do. Sample these rows from the original dataset and use it as bootstrap dataset number I, you could say. And then I create X and Y, and I do this CVGLMNet just as before, right? But now using these dataset. And now I get a minimum MSE, and this is the code for detecting for which lambda do I have the minimum, and which of the lambdas are this. I should perhaps have called this not IDX, I would call it IDD instead, just to not confuse it with the IDX up here. That was a better choice, I think. This is which lambda value is giving me the minimum MSE, and then I look at the fitted values for that particular choice of shrinkage here, right? Which variables, how is the regression coefficients looking like here, right? And some of them are 0, right? 3 of them I can see in this case, because only 6 of them are selected. But I just collect the regression coefficients straight away. I'm really just interested which one of them are 0, but okay, I collect the values and I return them. So this is my alternative function now, and then I run the bootstrapping as before. I use this again to run the bootstrapping, and notice now I only used 100 samples because this is sufficient now. I'm not going to construct a confidence interval. I'm not going to make a confidence interval. I'm just want to count how often among these 100 repetitions are each variable selected. How often is each variable selected? So if I run this here now, this GLMNet cross-validation will be done 100 times, so it takes like a few seconds. And then I want to look at this here again, right? We saw that previously. This is sort of the main output. So I copy it into this boot result here. We can actually have a look at it. So now I can see here for each row I have a new bootstrap sample, and here are the regression coefficients, right, for the first bootstrap sample. And then we can see in this case 2 variables were deselected. So 7 were actually selected here. Yeah, this is the intercept, it's never selected. And in the second choice, this one was not selected, right? And the same 2 are so these 2 here are deselected again. But now some others are also deselected, right? So if I sort of go down the column here now, I can sort of count how often is this for regression coefficient 1. How often is this 0? How often is it, or how often is it not 0? How often is it selected? That's exactly what I'm looking for now. So now I make this matrix with some column names here and so on. And votes. Here I simply count how many times is it not 0, right? Down each column. So this is now the boot result. And then this votes, I can just plot it here. Let me just plot it. Here we now have an impression of how these variables are sort of selected, or this is sort of their effect, you could say, on the price. And we can clearly see that year is selected quite often here, almost every time. And this kilometer is also, but notice this age is not so often selected. And we happen to know that age and year is actually the same thing. And this is of course because now I used alpha equal to 1 here. I used a pure lasso. And then in many cases year is selected, but for that reason age is not selected. And this is a bad sort of behavior, I would say, from the pure lasso, because these two variables should be selected or deselected together since they are correlated. So let's change this now to 0.5 and run the whole procedure again. So now we use elastic net instead of lasso. It takes some seconds. And then we have a new figure here. And notice now, year and age are both selected frequently, almost every time, together with this kilometer. So now we sort of see that, okay, these three variables we should study further. And then we will soon discover that these two are actually just carrying the same information. There's a confounding effect here. But we would not have discovered that if we were sticking to this, because then we would only select year and this one, right? And we would never realize that this is actually just as important as this one up here, right? So that's the benefit of the elastic net compared to the lasso.